안녕하세요 여러분, 혜리입니다. So in the last video, we have finished all the methods to integrate functions for HO students. So we have seen integration by substitution with some further trigonometric identities like reciprocals, and also we've seen how we could use the inverse trigonometric functions to integrate some quotient form. And also we learned integration by parts using product rule. So now we are going to focus on applications. So application for HL students. So if you're in SL or IGCSE student, if you're IBSL or IGCSE student, you don't have to watch this video. So for HL students, let's start with what you have to do. So first, we're going to start with area enclosed by the curve and the y-axis. So in the previous video when I talked about the basic application, we have seen the case where the area is enclosed by the curve and the x-axis, right? But now we are going to see the case with the y-axis. So the function will be like this. So x in terms of y. Note that it doesn't necessarily, the equation will not be given like this. So most of the case, it will be given like y equals fx, the normal form. But what you have to do is that you have to rearrange this into x equals to in terms of y. So basically you need to find the inverse function in order to do this, okay? But before that, let's see how it works. So we are looking for the area enclosed by the curve and the y-axis. So basically we are looking for this area. Then let's try to use what we have done for x-axis. So this is clearly an example of definite interval as well. So let's say the boundary is restricted to a to b. Then what we do is that first we make some rectangles, right? So let's call these as y1, y2, y3, and until yn, let's say. Then, as what we did, in order to estimate the area, what we can do is that first we find the width of the rectangle, and then in order to find the area of this rectangle, we have the width and we also need the length, right? But what is this length? So in this case, okay, let's say we use the length for y1, okay? So y1 and then y2 and so on. So that will be fy1, right? Because this is how the function is given. So fy1, this x value will be fy1 because f equals to x equals to a function of y. So that means if we know that this value of y, and if we substitute it, then we will have the value of x. So this will now become the length. So width, length, right? And we have this. And then plus doing the same thing, y2 minus y1 times fy2. So width, length. So that's the area of a rectangle, right? And then we add all the way until b minus yn and fyn. Okay? Now we have again we have too many variables. So let's say b minus a over n as delta y. So all the width here, we call it as delta y. Then this equation will be fy1 times delta y plus fy2 times delta y, and all the way until fyn times delta y. And again, this is this is the approximation. So in order to find the exact area, what we do is that we make infinitely many pieces of rectangle. And how do you write that down? We use the concept for limit, right? So limit when n tends to infinity, and also these are all in sigma. So sigma from k equals to 1 to n, fyk times delta y. And we already know how this Riemann sum can be written in terms of integrals. So integral from a to b fy dy. Because this delta y, when n tends to infinity, then this delta y approaches to 0. That means it becomes dy, right? So that's what we have. So as you can see, it's exactly the same. So what I mean by exactly the same is that the method of finding the area is exactly the same as what you did for the x-axis. So let's try an example. Let's say we have y squared equals to x plus 9 from and enclosed by x equals to 0 and y equals to 5, let's say. Now the main concern for this application is sketching. So I'm pretty sure for the x-axis, the previous example applications that we've seen with SL, that should be fine, right? Because it's just simple sketching. But now it's a bit different. So we have y squared equals to x plus 9. Don't change this into y equals to plus minus root x plus 9. Don't do that. What we can try to do is that we write this we write this x in terms of y. So that's what we have, right? Then how do we sketch this? It's not that hard. So this is x and this is y, right? One thing, we clearly know how to sketch this, right? That means x having roots x-intercept as plus and minus 3 and y-intercept as negative 9, right? Then for this one, just think as like this. So the x-intercept is negative 9, right? Then what about the y-intercept? 3 and negative 3, right? And that means that's how the graph looks like. And what we have to find is we have to find the area enclosed by x equals to 0 and y equals to 5 as well. So we don't really need this negative part. So I'll just quickly sketch it again. So that means we have negative 9 here. And let's say this is 3 and this is 5. Then that means the graph would look like this, right? So basically we're finding this area and this area. And again, as what we did for the previous case with x-axis, so look at the graph like this. So remember how we find the area enclosed by area under the curve with y-axis. So now this one, we see that the length becomes negative, right? All the length becomes negative. So that means we put negative sign in front to make all these lengths become positive to find the area, right? So this case, so from 3 to 5, it's all positive. So it shouldn't matter. So we integrate this function like this, right? Because x equals to that, right? So remember, x equals to fy, a function in terms of y. So we make it like this, right? Then again, like what we did, we let x be a function of y and then integrate that, and that will yield this area. Okay, then what about this black area? Well, it's the same, but we are just putting negative in front. So we're integrating from 0 to 3 y squared minus 9 dy, and it should be simple. So I'm not gonna carry out the calculation because it's a bit time consuming. So this shouldn't be hard. You're just basically integrating this in terms of y. So that will become 1/3 y cubed minus 9y, and then you just substitute these two values, and the same 1/3 y cubed minus 9y, and substitute these values, and then find the area for this, and then that's it. Add them together. So that's it for the first basic application. So now what we are trying to see is we are going to see the case where we have to find the area enclosed by two curves and the y-axis. Alright, so it's the same as what we did for the x-axis. So let me just directly move to an example. So let's say we have something like y equals x minus 2 and y squared plus 2y equals to x. So again, the main concern is sketching, because remember, when we have to find the area between two curves, we have to find the intersections, and we have to find which curve is above and which curve is below, right? So let's try to sketch this first. So again, that one should be very simple, right? So that one, that means the y-intercept is -2 and x-intercept is +2. So it's a straight line like this. And y squared plus 2y equals to x. That means it's this. So the y-intercept is 0 and -2 here. Then what about the x-intercept? It's just 0 as well, the origin, right? So that means it looks like this. So that's how this curve looks like, and this is a simple linear function. Okay, so area enclosed by these two curves, that means we have to find this region, right? So one tip to give you is that try to look at the graph like this. Which graph is above? The linear, right? And the quadratic is below the linear function, right? And it's not a function, sorry. So it's below the quadratic equation, right? The graph of this quadratic equation. So what I'm trying to say is that the linear function is above the graph of this quadratic equation, and this is not a function, as we recall the definition of function. So what we can do to find the area is exactly the same as what we did for the x-axis. So first, find the intersections. So y squared plus 2y equals to x, and you equate this with y equals to x minus 2. But y equals to x minus 2, why don't we write this like this? And then let this equals to that. So y squared plus 2y equals to y plus 2. So y squared plus y minus 2 equals to 0. So y plus 2, y minus 1. So that means the intersection is at y equals to -2. Makes sense, right? And y equals to 1. So that means this point is 1. Now we know the boundary, and we know which function is above. Then apply what we know. So from -2 to 1, this function is above, right? So we put y plus 2, and we subtract this. y squared plus 2y and integrate in terms of y. So it shouldn't be that difficult. So that's the area that we want to find. So that will be, what is it? So 2y, y minus 2y, so minus y, that means negative half y squared. And then we have negative y squared, so negative 1/3 y cubed. And we evaluate from negative 2 to 1. So when we insert 2, we have 2 minus this, and then subtract the case where it's negative 2, so negative 4, and then negative 2, and plus 8/3. So 2 minus 5/6, and then that will be 6 minus 3/8, so 8 minus so 9/2. Okay, so that's how we can find the area between two curves. So again, it's the same. You find which curve is above which, and then just follow what you know. So if we want to generalize this, again, the area between two curves will be from the two intersections, and then we have the function above. Sorry, so it should be in terms of y, and function below, and then dy. That's it. So this one is above, and this one is below. Okay, so the key thing is to sketch. Okay, so that's it for area between two curves. So now, before we move to another application, I'm going to expand a bit more with area between two curves. But instead of just any two curves, we're going to look at some specific case where we have to find the area with inverse graphs. So graph of the inverse. So we all know how to sketch the inverse function, right? We have already learned that from the properties of inverse functions. So I'll just quickly give you an example. So for example, let's say, actually, should I just go for the? So for some, as you already know from inverse functions, for some cases, it's impossible to find the inverse equation. So for example, if fx is x cubed plus 2x, then can you find the inverse? Probably not, right? So, but what if we have to find the area with the inverse function? So then how can we do that? So what we can do is that, so for example, the question may ask you like this. Let's see. So f1 equals to 3 and f2 equals to 12, right? So let's say you have to find the inverse from 3 to 12, let's say. Then again, as I said, it's impossible to find the equation of the inverse. So that means how can we find the value for this? So let's try to sketch this a bit. Actually, sorry, I'll just change to -2. So because I don't want to use the negative part. So when we evaluate for 2, that's 8 minus 4, so that's 4. So yeah, we want to evaluate this integral. So for example, let's say this curve look like, so it has a repeated root at, oh actually, okay, so √2 and -√2. So this is how the curve would look like. So yeah, this is how it looks like. So we want to find this area. That means we have to sketch. So using this cubic function, we can sketch the inverse of this. So that's root 2, and this is negative root 2. So it will look like this. So this is how the inverse looks like. So now we want to find the area from 3 to 4. So that's the inverse, right? So 3 to 4. So this part, that's what we want to find, right? And again, it's impossible to find the equation. Then how do we integrate this? We can use this to do it. But how? So we see that if we want to find this region, that means we are finding this region from 3 to 4, because it's exactly symmetrical. So this one, right? That's how it looks like. 3 to 4, 3 to 4, and this region, it's the same. Then how do we find that region? What we can do is that first, you know this point, right? So this should be 2, right? And this should be 1. Then what you can try is that from this entire area of rectangle, we can subtract this part by integrating this. Integrating this should be very simple, right? And we can subtract this rectangle, which is 1 times 3, so 3. So let's see how we can find this again. So I'll just quickly write it down again. So I understand that this is a bit confusing. So this part, so what we want to find is this, right? And that is this function, right? And this is 1 to 2. Okay, wait, 1 to 2, but how can root 2 be here? Alright, I'm really sorry, it's a wrong sketch. So it should be 1 to 2 somewhere here, but alright, forget about this. So alright, I'm really sorry to make this confusion, to cause this confusion. So let's just use different points. So let's say 3. So F3. So that's 27 minus 6, so 21. And F4. So that's 64 minus 8, so that's 56. So again, I'm really sorry to make this confusion. So we're trying to see the area from 21 to 56. Okay, so 21 to 56. Okay, so that should be 3 and 4. So this is not 3, instead this is 21, and that is 56. Okay, yeah, sorry. So again, this is 3 and 4, so this is 21 and 56. Yeah, this is why we have to care about some scale. So yeah, sorry, but anyway, so we want to find this red region. So what we can do is that from this entire rectangle, we can subtract this smaller rectangle and this region. Then how do we find this blue region? What we can do is that blue region is simple. Why? Because we're basically integrating from 3 to 4. dx. So it's a very simple polynomial we have, right? So that means 4 to the 4, but we cancel 1 4, so that's 64 minus 16 minus 81 over 4 minus 9. So that would yield, I hope I don't make any mistake. So that's the area for this blue part. Then we're done. Why? So the entire region, entire rectangle, is 56 times 4, right? So that's 224. Wait, did I make any mistake here? Okay, yeah. And this smaller rectangle is 21 times 3, 63. Then the red region would be 224 minus 63 minus 174 over 4. So that will be 161 minus, okay, so that should be the area of this red region. So see, we can see that we don't need the area of sorry, yeah, that's so that's how we could find it. So we can see that we don't need the equation for the inverse to find the area. What we can do is that we can just use a sort of geometry, so using the graph of the functions to find the area. Okay, so that should be fine for this. So okay, I understand that this is a very hard example, but I'm going to do one more example because this one is actually a bit important, and I have seen a lot of students having questions involving this inverse in their mock exam, or at least in their unit test for calculus. So let's try another example, but this case I've already prepared it, so the number is nicer than the previous one. The previous one I just made it too fast, so I didn't confirm it. So find this. Alright, so for this question, you don't have, the function is not defined. Oh, sorry, so this is 4. So f4 equals to 7. So the function is not defined, and we want to find this region. Then, although the functions are not given, let's try to kind of estimate how it would look like. So f, this is 2, and let's say this is 4, then so that's 4 and that's 7. Okay, the graph shouldn't, you don't have to make the graph in scale, but it's good to make it as long, so it doesn't have to be like perfectly on scale, but try not to make it like very weird. Okay, so that's the given information, and using this information, so G is the inverse, so using the inverse property where the domain of the original function becomes the range of the inverse, and the range of the original function becomes the domain of the inverse, right? So that means G4 equals to 2 and G7 equals to 4. So that's 4 and that's 7, so that's 2 here, and then 7, 4. So that should be somewhere here. So we don't really know how the graph would look like, but at least we know that it's something like, it should be something like this for fx, right? And then it should be something like this for gx, right? So we have this, and then what the area that we are trying to look for is that for fx we want to find this region, and for gx we want to find this region, right? That's what we have, that's what we want to find. So again, as I said, I mean, not as what I said, but for this question we don't know the equation, right? Then how are we supposed to find the area? So don't try to rely on integration. So what we try to do with so what this question is basically asking is that just find the area under this region, right? I mean, area of these regions. So then why don't we try not to use integration to find the area? How? So for example, not for example, but for this one, it's integrating from 4 to 7. But this is the inverse of f. That means this blue region will be exactly the same as this, right? Then as what we did just now, from this entire rectangle, we can subtract a small rectangle. So the entire rectangle is 4 times 7, which is 28. And the small rectangle is 2 times 4, which is 8. Therefore, this answer for that, it'd be 28 minus 8, so 20. Okay? So that's how we can use integration, inverse function to find certain area under the curve. Alright, so that's it for the application using the inverse. So now what we can do is we can try the volumes, but we've already done it, right? Volume of revolution, but we've done it around the x-axis. Now we're going to do around the y-axis. So again, it should be the same as what we have done for x-axis. So don't just treat like x-axis and y-axis as exactly different thing. You can just rotate it. Then x-axis will become y-axis, right? So you can just rotate it to understand the sketch, okay? So for integration, especially for applications of integration, sketching is very important, as you have just seen for the inverse and also the area under the curves. So as long as you can sketch it properly, then it wouldn't be that difficult. So let's say we have like a function. It doesn't really have to be a function, so equation in terms of y. So x in terms of y, like this. And then we want to find the volume revolved 360 degree around the y-axis. So as what we did for the x-axis, what you can try to think is that you're trying to add infinitely many cylinders, where those cylinders are as flat as just 2D circle, and you're just adding up all the cylinders to find the volume, right? So in order to find the area of the volume of the cylinder, what do we need? We need the base area and we need the height, right? So how do we find the base area? So first, the base area would be all these, so let's call this as so let's say this is A and we want to find until B here. Then let's say we have like y1 and y2, y3n all the way until yn. Okay, then when it's y1, then what's the radius? Radius will be this x value, which is gy1, right? And when the y value is y2, then similarly this x value will be gy2, right? And it's the same until this, where it's gyn, right? So the radius are gy1, gy2, gyn, like respectively. And then what about this height? So we can also define height like from y, like a to y1, and then y1 to y2, y2 to y3, and so on, right? So we can kind of approximate the volume by adding up all these small cylinders. So the first small cylinder would be gy1 squared and pi, so pi r squared, right, this base area, times the small height, which we can write it as y1 minus a, and then plus pi times gy2 squared and y2 minus y1. So that is the small height, and that's the base area. So this entire thing, the product of these two, would yield the volume of a very flat cylinder, right? So we add all the way until the last term, the last cylinder, not called, but so b minus yn. So it's a bit hard to see, but you'll have I'll post this note as well, so you can just download it. So again, there are too many variables, so what we can do is that we let each height as this, so that means all these small heights can be replaced by delta y. So this would be, so we can take out by common factor. So all this become delta y, right? So we take out by delta y. So basically we're adding all these squared values all the way until the last area of the base. Now we can use sigma notation. So from k equals to 1 to n, g, y, k, and then squared. So again, in order to find the exact volume, we use limits where n tends to infinity. So that means we're dividing this entire volume into infinitely many small, very flat cylinders. Okay, so sigma k from 1 to n, gyk squared delta y, and then we have pi. So what we have is that this sigma, again, using the definition of integration, it's the integral. So the boundary is from a to b, right? A to b, and this is simply gy, and delta y becomes dy, right? Oh, but note that this is gy squared, so we squared it, okay? And it's dy, and then we have just pi in front, okay? So that's it for it. That's it. But I know that the formula on your textbook and the formula booklet for IB will be like this. So some may ask why gy becomes x, because that's what we did, right? So x equals to gy. So just simply replace gy as x, and that's all. That's fine, right? So that's why we have this formula, okay? So let's try an example, a very simple example. So let's say we want to find the volume enclosed by this region, and then revolved 360 degree around the y-axis. So quickly sketching this. So sketching shouldn't be difficult by now. So we're trying to find from 2 to 4. So this part, right? So that means it kind of looks like the shape would be something like this. So what we're finding is like this volume of this. Okay. Well, so for this one shouldn't be that difficult. You can, to be honest, you can find the volume of this shape solid by finding the volume of the entire thing and then subtracting this small cone. But let's try to use integration to do this. So revolving 360 degree, rotating 360 degree around the y-axis, then you can just instantly recall this formula if you have understood all these steps. Okay, so I mean, even if you don't understand all these steps, you can just still memorize it and then do it. But sometimes you may not be able to like solve the questions properly when the equations are very difficult, or sometimes it's very indirect. And what I mean by indirect is that I'll post one question on the sample test for this video, and you will see what I'm trying to say. Okay, so but anyway, so what I want to emphasize is that please understand the concept and understand why you have all these formulas. If you understand that, then it's gonna be much better for you to apply. Okay, so we have this, and we already know the boundary. It's from 2 to 4. So we need x squared, right? That means we need the equation of x in terms of y. And it's very simple. Finding the inverse of linear function is just a piece of cake, right? So we have this. So that means we have I hope I didn't make any mistake. But yeah, so again, I'll skip this basic arithmetic. Yeah, so you can just continue, okay? But so that's how we can find the volume of revolution around the y-axis, okay? Then is that it? Unfortunately, no, because we also have to try. I'll not call it as 5, but so okay, I'll just call it as 5. So volume of revolution around the y-axis, where the region is enclosed by two curves. So like what we did for the volume of revolution around the x-axis, okay? So again, the idea is the same. So you look for the bigger volume and then you subtract the smaller volume. So in order to do that, you need to find which function is above and which function is below. So it's exactly the same as what we have to do for area enclosed by two curves. Okay, so I'll just directly go for an example. So y equals to x squared, and let's say it's restricted to x greater or equal to 0, and then it's bounded by x equals to 0, which is the y-axis, and the region is also enclosed by a linear function x plus 2. So let's try to sketch this. So we just need this part, right? This part, and this region is enclosed by this linear function as well, right? And then y-axis. So we're looking for this, right? And if we revolve this around the y-axis, then what you will have is a volume like this. So basically a dome shape, a semi-sphere, kind of semi-sphere, and you subtract this cone. Okay, so I understand that it's a bit hard to see, so I'll just quickly sketch it again. So this is what we're trying to find. Okay, so that's y equals x squared, and this is y equals x plus 2. So again, as I said, you just need to find the bigger volume and then subtract the smaller volume. So, and what I mean by that is that we basically look for the function above and then we subtract the function below, like what we did for area. And so we have this, and how can we determine which function is above? Don't look at the graph like this. You have to rotate it first because you're revolving around the y-axis, right? So, and then you determine which one is above. And which one is it? The quadratic formula, right? So the not quadratic formula, quadratic equation. So the quadratic equation is above this linear function. That means we find the volume created by this quadratic equation, and then we subtract the volume created by this linear function. So that means we need the boundary, right? So in order to find the boundary, we find the intersection. So that means x minus 2 and x plus 1. So x equals to 2 or x equals to negative 1. So does that mean this is negative 2? I mean this is 2 or negative 1? No, because that's for x values, right? X is 2, not y. So in order to find this, we have to put it into the function again, okay? So basically we're trying to integrate from 0 to 4, okay? So we integrate from 0 to 4, and how do we do that? So one thing that you have to know is that, so first, from 0 to 4, we find the volume. Okay, so let's find the volume of the big one first. So the entire volume entire, it'd be pi, and with this boundary, and then x squared. But what's x squared? Y. So we're simply just integrating y. Okay, so it should be deadly simple. It's just 8, right? Then what about the other one? So one thing, do we have to integrate this from 0 to 4? Do you think we have to integrate from 0 to 4? And the answer is no, not necessarily, because we just need to integrate from 2 to 4, right? So from this entire volume, we're just subtracting this small volume, right? And that one, it's basically from 2 to 4. And does that matter? Yes, it does, because we're not considering where the part is negative, right? So if we integrate this x plus 2 from 0 to 4 around the y-axis, then what happens? So this is why the sketch is very important, because if we integrate this, sorry, it's not x plus 2, so it's x equals to y minus 2, so that means y minus 2 squared. But anyway, so if we do this, note that what happens is that so we are revolving this like this from 0 to 4, right? So that means from 2 to 4 we have this. But what about this? From 0 to 2, we have another region created. So you have to look carefully with what you're doing. Don't just apply formula. Don't do that. So think where to integrate. Don't just apply formula directly. If you apply the formula directly, then very likely you will not have the same answer. I mean the correct answer. So that's what we have to integrate. So that one will be So this is what we have to integrate, and I will. Oh wait, sorry. So I forgot pi here. I'll just. Oh, sorry. It's not from 0 to 4, right? It's 2 to 4. So. Have I done everything correct? Seems like. So this is what we have, okay? And what do? You subtract these two, and that should be it. So the volume that you want is subtraction of these two, so it should be this one, okay? So if we generalize this, what we can have is that the volume enclosed by two curves, you can again apply what you know. So F so this is above and this is below, but again you have to carefully look for the region that you're trying to integrate. And I'm sorry, I don't think I've shown you this, so you can check this like this, okay? I mean, you can check it. So that's it for the volume of revolution around the y-axis with two curves. So we're one last thing, then we're done. So it's not a big thing. So kinematics. So 6 kinematics. So there are not many things that you have to do for SL kinematics and HL kinematics for integration should probably almost the same. But one thing that you must be aware with the question type is that, so for HO students, you may have something like this. So for example, this question is from the Cambridge textbook, by the way. So this is the question. So given an equation of acceleration in terms of velocity, and the initial condition is given, and we have to show this equation. All right, so a lot of students, well, I have not seen many students who are able to solve this. So the reason why this question is treated difficult is because, again, the equation is not in terms of time. Because remember, if we integrate acceleration in terms of time, we have the velocity, nothing else, time, okay? And also if we integrate velocity in terms of time, then we have the displacement. But unfortunately, we have the equation of acceleration in terms of velocity, which means that you cannot integrate this by time directly. Then what can we do? So first, we know that acceleration is dv over dt, right? So dv over dt equals to v squared plus 4 over 2v. And we can see that we have to show this, right? And we cannot use this equation. We cannot use this equation to derive this, but we can kind of analyze it and then see how we could derive this. So as you can see, this equation involves t. But is there any t? Well, it does, as in denominator, but just t as in denominator, it didn't help a lot. And in fact, the reason why, if the acceleration if we integrate acceleration by t, the reason why we get velocity is because you see that dt cancels. So it's simply integrating 1 by v. So that's why we have velocity. So again, if we do this, well, for left hand side we have v, but we cannot do anything on the left hand side, right hand side. Then what we can do is that why don't we consider the reciprocal? And why don't we integrate both sides by v? Why? Because if we integrate this, if we integrate the left hand side by v, what we have is that we have time. Why? dv cancels, then that means we're integrating 1 by t. That means we have time, right? So the left hand side becomes t, and what we have to do is we have to integrate this function in terms of v by v. And clearly it's integrable because function is in v and then we integrate by v. That's very simple, right? And also we can either use substitution, but for this one we see that the numerator is the derivative of the denominator. That means it's simply ln v squared plus c, v squared plus 4 plus c. And since the inside of ln is always positive, right? V squared is always positive, so we can just ignore this modulus sign. Then what we have to do is we have to find c, and how do we find this? Use the initial condition. So initial velocity equals to 3, that means time equals to 0, and then velocity equals to 3. So that's ln certain plus c. Therefore, c is negative ln certain. That means we have the full equation, right, without any parameter, except for the variables that we need. So using the ln property, we can just group this together like this and change this ln into exponential form. Then rearranging this, we have v squared equals to 13 into t minus 4, and that's it. Okay, so that's it for HO applications for integration as well. So yeah, that's it, and good luck with your test with calculus.